Okay, in 16.2, we move beyond the Arrhenius theory for acids and bases, and we move into the Bronsted-Lowry definition. I always forget, it's just PD. Okay, so before we tell you exactly what the Bronsted-Lowry definition is, let's demonstrate where the Arrhenius definition begins to fail. If I take something like HNO2 and I react it with something like ClO2 minus the chlorite ion, this will be an equilibrium reaction with products of H, ClO2 plus nitrite NO2 minus. And nitrous acid is an acid, and chlorite ion is a base, but there's no H plus or OH minus, neither as a reactant nor as a product. And so Arrhenius theory really doesn't have anything to say about this reaction. Under Arrhenius theory, we wouldn't be able to justify calling this an acid-base reaction. Neither of these is changing the amount of H plus or OH minus in solution. And so we need to have a more comprehensive theory to describe what is an acid, what is a base in the context of reactions like this. And so that's where Bronsted-Lowry theory comes in. And Bronsted-Lowry theory defines an acid as a proton donor. That is a compound which will end up giving a proton to its reaction partner. And if we think about HCl plus H2O forming H3O plus Cl minus. This was the example of a strong acid that we used when discussing the Arrhenius theory in the last section. We defined HCl as an acid because it increased the concentration of H3O plus according to Arrhenius theory. Well, here we can recognize that that hydrogen has been donated to the water in order to make H3O plus. And so HCl is an acid according to Bronsted-Lowry theory as well. Well, that's a good thing. Any theory that called hydrochloric acid, that didn't call it an acid, would be a bad theory. So acids are proton donors. The really great innovation for Bronsted-Lowry theory is in framing bases in terms of protons as well. Hydroxide doesn't even make an appearance here. A base is a proton acceptor. So let's go back to an example from the last section. Ammonia, NH3 was a weak base. NH3 plus H2O was in equilibrium with NH4 plus OH minus. Now, Arrhenius theory says, well, we've got OH minus as a product, and therefore NH3 is a base. But Bronsted-Lowry theory doesn't care about OH minus. What Bronsted-Lowry theory notices is that a hydrogen has been donated to the ammonia. It went from NH3 to NH4 plus. And so that made NH3 a proton acceptor, and that made NH3 a base. And this definition is going to be a lot more versatile. Let's look at the reaction that we opened with here. Sorry, that's my chair. Okay. Let's look at the reaction that we opened with here. HNO2 plus ClO2 minus in equilibrium with HClO2 and NO2 minus. So where has there been an exchange of a proton? Where has one chemical donated a proton and the other one accepted it? Well, we see here that the ClO2 has gained a proton and that the HNO2 has lost a proton. I could diagram this reaction as being something like that. And so which of these is the acid and which is the base? Nitrous acid, perhaps not surprisingly, is the acid, and chlorite ion is the base. And now we have a good solid theory for calling this reaction an acid-base reaction, even though there's no H plus or OH minus present anywhere. Let me go ahead and erase this, because there's something really interesting going on with this reaction. It's a reversible reaction. It reaches equilibrium, and the products can react to regenerate the reactants. So let's look at this reaction in reverse. If we're thinking about it in reverse, it looks like HClO2, which is chlorous acid, is donating a proton to nitrite ion. And so that makes this also an acid. And this, the nitrite ion, is a base. And so for this reversible reaction, it's really easy to justify calling this an acid and that a base, because in going in the reverse direction, the chlorous acid actually is donating a proton to the nitrite ion. Well, that sets up this really interesting relationship between the reactants and the bases. Of course, nitrous acid and chlorite ion have a relationship as reaction partners. But nitrous acid and nitrite ion have a relationship of being just one hydrogen different from one another. The nitrite ion is the same as nitrous acid, but it's missing an H plus. And so we call these two conjugates of each other. Or we can call them a conjugate pair. They're related, and it's going to be really important to keep track of these sorts of relationships as we begin to talk about acids and bases in more complexity in the future sections. And of course we can note that chlorite ion and chlorous acid are also linked in this way. They differ only in by an H plus, by one proton. So these are also a conjugate pair. Conjugate pair. So I could look at a chlorous acid and say, what is the conjugate base to chlorous acid? And you would look at it and you'd say, well, what does HClO2 look like if I remove H plus from it? It looks like ClO2 minus. And so that is the conjugate base to chlorous acid. And if I looked at nitrite ion and I asked you, what is the conjugate acid to nitrite ion? You'd say, well, what does nitrite ion look like if I add an H plus to it? We'll add an H, and the plus undoes the negative charge, and we get nitrous acid. HNO2 is the conjugate acid to nitrite ion. Now, one of the things about conjugate pairs is that they share a certain amount of strength between the two of them. We've talked about strong acids and weak acids, strong acids and weak bases. Well, not all weak acids are going to have the exact same acid strength. Some of them will ionize only 5%. Some of them will ionize maybe 10 or 20%. Some of them will ionize only 1%. They all have varying strengths. So some weak acids are truly weak, and some weak acids are getting to be pretty strong. They're almost maybe on their way to being a strong acid. And so conjugate pairs have this inverse relationship where the stronger the acid is, the weaker the conjugate base will be. So if I have a weak acid that's particularly strong, maybe it's one of those that is almost a strong acid but not quite, then I can tell you that its conjugate base will be a particularly weak base. And if I have a base that is particularly strong, then I can tell you that its conjugate acid is going to be particularly weak. So if you have a middle ground acid, then its conjugate base will also be in the middle. And again, we'll deal with this quantitatively or with real numbers in a little bit after we've built up a few more tools. But I want you right now to already recognize that it's like there's only so much strength to go around, and it needs to be split between the two members of a conjugate pair. So the stronger one is, the weaker the other one will be in consequence to that. Okay, I want to put up two reactions. We actually already had one of them, NH3 plus H2O in equilibrium with NH4 plus OH minus. And then I want to put up HNO3 plus H2O. And that's going to be H3O plus NO3 minus, nitrate ion. So I want to show two principles in here. So for these two reactions, can we identify the acids and bases and the conjugate pairs? Well, here ammonia, we already saw, is going to be sort of taking a hydrogen from the water. So that makes water an acid, and ammonia a base. And this could go in reverse, and so that H could go over there, and NH4 plus is the conjugate acid to ammonia, and OH minus is the conjugate base to water. So here are my conjugate pairs, like that. Let's do the same thing for HNO3 and H2O. So it looks like HNO3 is donating a proton. That makes it an acid. You may recall that it's one of the strong acids. And the water is receiving that proton, so it is a base. And going the other direction, looks like H3O plus would be an acid, and NO3 minus would be the base. And so here we have a conjugate pair. Oh, there we go. And here we have a conjugate pair. Okay, so 2 points I want to make with these two reactions. First of all, is water an acid or is water a base? And the answer is it depends on context. It depends on what the reaction partner is. Water is capable of donating a proton and being an acid. Water is capable of accepting a proton and being a base. Water is versatile, and that versatility is really important to how acid-base chemistry works. And the whole next section is going to talk more about water, so I'll just leave that there. Then the other question is NO3 minus the conjugate base to nitric acid? Is NO3 minus really worth being called a base at all? You know, up here we have an equilibrium reaction that goes in both directions. Ammonium is the conjugate acid to ammonia because it really can and does donate a hydrogen in chemical reactions. HNO3 is a strong acid, and so we have a single-headed reaction arrow going all the way to products. And although we can talk about nitrate taking the hydrogen from the H3O plus and being a base in a theoretical sense, we never actually observe it happening in nature. This reaction goes to products and it stays there. And so nitrate is the conjugate base to nitric acid, but it's kind of a base in name only. Nitric acid is one of the 7 strong acids. And remember how the conjugate pairs kind of have to share a limited amount of strength between the two of them? Well, the strong acids took it all. The nitric acid has all of the acid strength, and that leaves its conjugate as having essentially no basic strength whatsoever. And so is nitrate a base? I would say nitrate is not a base. The only time I'll write the word base under a nitrate ion is in the very technical sense, in the context of it being the conjugate base to nitric acid in a particular chemical reaction. We can say the same thing for strong acids. So HCl, hydrochloric acid, its conjugate base is a chloride ion. But is a chloride ion really a base in the sense of, like, are we ever going to observe it undergoing reactions where it accepts a proton from its reaction partner? The answer is no. It is such a weak base that it's just not really a base at all. All right, one last thing to talk about really quickly. There are a couple of acids that are multiprotic. They're able to donate more than one hydrogen. So we've already seen one of them, H2SO4. That's sulfuric acid, and it's one of our 7 strong acids. I'm going to put up here sulfuric acid's little sister, H2SO3. That's sulfurous acid. And sulfurous acid is a weak acid, so it's in equilibrium. And I won't write like a full proper chemical reaction here. I'll just show the conjugate acid-base pairs. So H2SO3, what's its conjugate? It would be HSO3 minus. And so this is an acid, and here is its conjugate base. But HSO3 minus can also donate a proton. And what would be the conjugate to HSO3? That would be SO3 2 minus. And these are linked as a conjugate acid-base pair. But HSO3 can also act as an acid, and it has its own conjugate base. And so HSO3 minus is like water in that it's able to act as either an acid or a base, depending on the context, depending on its reaction partner. We can call these types of things amphoteric or amphiprotic. I think amphiprotic is probably the better term for this class. So amphiprotic species are able to either give or receive a proton. Here's another really good example. H3PO4. Well, that can donate a proton, and we're left with H2PO4 minus. And then we're going to have HPO4 2 minus. And then we're going to have just PO4 3 minus. So in this series, we have a triprotic acid that's able to donate 3 protons in series. And at the far end here, we have a tribasic base that's able to accept 3 protons. And in the middle, we've got some amphiprotic species. H2PO4 minus could go either way. HPO4 2 minus could go either way. One last thing I want to say about these. If if these are both acids, which one is stronger? Well, this is the strongest acid in the series. Okay, and just like H3PO4 is the strongest acid, HSO4 is weaker than HSO3 is weaker than H2SO3. H2PO4 minus is weaker than H3PO4, and HPO42 minus is weaker still. And then over here we have the strongest base in the series. So sulfite ion is a stronger base than hydrogen sulfite. Phosphate ion is the strongest base. Phosphate ion is a stronger base than hydrogen phosphate or dihydrogen phosphate. And this is the middle base, and this is the weakest base in the series. H3PO4 is not a base at all, just like sulfite and phosphate are not acids at all. Okay, so anyway, when we have these species involved, we need to be just a little bit more careful, like is this an acid or a base? And when we're talking about its strength, are we talking about its acid strength or its base strength? And we just need to be careful to sort all of that out and not confuse ourselves.